Hello, everyone. I'm Paul Musto, and welcome to Startups, a podcast where we talk to startup entrepreneurs and learn how they turn great innovative ideas into successful, profitable companies. In this episode, we are speaking to a company developing new forms of propulsion for space satellites. Space satellites are being launched and deployed at a rapid pace and in high volumes. As we will hear, this small company is making its impact on space satellites and will be part of a launch in the very near future. My guest today is Dean Massey, Director of Research at Apollo Fusion. Dean will share his story of Apollo and provide some insights on the growing deployment of space satellites. Before we begin, at the end of the session, please let me know what you think of this episode. You can leave a review on Spotify or Apple Podcasts or email me directly at paul.musto@siemens.com. So let's get into it. Welcome, Dean, and thank you so much for taking the time to speak with us today. Would you give our audience a little bit of an introduction to yourself?
Sure. Thanks, Paul. I really appreciate this opportunity to kind of give you guys some insight into this pretty dynamic industry. As you mentioned, my name is Dean Massey. I'm the Director of Research at Apollo Fusion, a position I've held since, Apollo's inception way back in 2016 when we used to be a fusion company, but I'm sure I can tell you guys that story a little bit later.
And tell us about Apollo Fusion and the mission that you and your team have embarked on.
Apollo's mission is to enable companies to have access to propulsion systems and therefore, more enabling missions that they wouldn't have access to in the days prior to new space. So this includes not having to have a very large propulsion team yourself, being able to just essentially buy something off the shelf, bolt it to your spacecraft, and be on your way so you can actually focus on the payload that's going to generate the money for you, be it, a radio for some kind of comms or a camera or probably some other ideas we haven't even really thought about. That's not to say that it's excluding us from the prime market as well. They're just much more established and they know the questions to ask. And so it's a little bit easier, but they're also more established. So we have to establish ourselves in their eyes to some degree.
You mean when you talk about the prime market, you're talking about the prime OEM company that's launching the rocket?
Not so much that. It's more the satellite provider primes. So the Boeings or, the government or whoever, whatever contractor is working on that. So we can propel spacecraft of any size, but we're trying to make up for it in volume. So, and there's just many more opportunities in the small sat, the 400 kilogram range sort of market. So that's kind of the target market that we're after.
And why don't you tell us a little bit about yourself? In the last conversation we had, you kind of told me about your journey into Apollo and didn't really start off as creating propulsion systems for satellites. So why don't you tell us a little bit about that story?
Yeah, sure. I mean, it's a neat and kind of quintessential Silicon Valley story, if you will. As the name suggests, Apollo Fusion was a fusion reactor company. So before it was even called a fusion, we didn't even have a name. But Ben Longmire and Mike Cassidy got together, and Ben had an idea for kind of a prototype fusion reactor and stuff like that. I was living in Texas at the time, and it was just some lazy Sunday evening when Ben, who'd been a former colleague of mine, just called me up and was like, "Hey, do you want to move to California and work on fusion?" I was like, yes, of course I do. Like, who wouldn't want to do that? And I mean, oil was okay, but I mean, if you recall, there was a huge downturn in the market at the time. So looking for something different to sink my teeth into, and Northern California in the summer, there's few places you'd really want to be. So we kind of embarked then on. It was a fantastic summer. So I guess we really hit the go button. I would say mid-June of 2016. Again, it's almost comic how stereotypical it is, because we were working in a garage in a cul-de-sac, and the weather was perfect, and we were just working on a fusion reactor barefoot with the garage doors open, like everyone else in the neighborhood was doing. So, but it was just in addition to being a lovely summer, it was also just kind of the genesis of a lot of neat ideas that we would take with us. Not only to the propulsion market, but even as we eventually aged out of the fusion. So I guess that's a foreshadowing of what I'm about to say next. We were getting decent results to the point where we're justified as seeking out some venture capital. So Mike worked his magic and secured us some funding, so we're actually able to move out of the garage, which was kind of bittersweet. It had a pretty low ceiling, so it was nice to be able to fit something bigger into the space. So yeah, we made the move to our current office in Mountain View and started looking at how we're going to improve the yields, the neutron flux that we were so desperately after. And along the way, what we did is we grew the team pretty substantially. We brought on, honestly, an amazing team of researchers and engineers, most of which are actually still with us to this day. So, we were doing staff nuclear engineers, experts in nuclear graphite, data acquisitions, experts, propulsion experts, machine learning experts. Like at one point, we were actually doing machine learning on fusion reactors, essentially 24/7. So we'd turn off the lights and go home, and it would sit there and work its way through the variable space, and then we'd check in the morning to see kind of where it landed. And that process, repeated itself pretty extensively. But as time went on, it became kind of clear that it wasn't going as well as we had hoped. It was kind of in the back of people's minds. So we started reaching out a little bit more, trying different kind of technologies, iterating yet again on the reactor. I mean, in the whole time, we were just kind of making subtle changes all along the way. So it wasn't just all done in software. But eventually, it was just like, okay, this is not really gonna work, guys. And I don't know if the audience is aware, but fusion's actually pretty tough. So this wasn't really a surprise to ourselves and to anyone watching. But I mean, we gave the old college try and definitely did about 10 years worth of work in about 9 months. But at the end of the day, we decided to pivot because the other options were, of course, just ceasing operations and giving the remainder of the money back, or pivoting to something that was also possible. And we had assembled such a great team, like there really wasn't anything we couldn't do. It was more like, okay, let's take a quick look at the markets, what's in our toolbox, and what are the potential customer pain points. So we ended up settling on Hall effect thrusters. And the interesting part about that is that's actually how I knew a lot of the teams, because we all worked on Hall effect thrusters in graduate school. So, which means that our vacuum facilities that we had built for the fusion reactor were basically tailor-made to produce Hall effect thrusters, because that's all we knew how to build to begin with. So it was a very, very easy transition for us. It was only a matter of weeks before we had a functioning Hall thruster going. And after that, I guess the rest is pretty much history.
Okay, Dean, for us common folk, can you give us kind of in layman's terms what a Hall thruster is?
Hall thrusters are not really anything new. I mean, they've been around since the 1960s. And what it is a plasma propulsion device. So not unlike the twin ion engines, the TIE fighters from Star Wars. A little bit different technology, I would say a little bit less elegant. But what they do is allow you to, take in solar power, ionize a inert, or I guess it doesn't have to be inert, but a neutral gas, and then accelerate it electrostatically out of your spacecraft, generating it's a very small amount of thrust, but you're in space, so it doesn't take much, and these things can operate for thousands of hours. So like slow and steady definitely wins that game.
Thank you. I didn't really understand that, so thank you very much. So just to kind of take a step back a little bit, so many of our listeners may not even be up to date with kind of the trend of satellites and all of the initiatives underway to significantly increase the number of satellites in space. Can you give us a little bit of your perspective on what's happening and what's driving the need, and what do you see happening into the future with satellites?
Sure. I mean, to look to the future, I guess it's best to almost take a quick look at the past and what the satellites looked like before this. I mean, we've been launching satellites into space, of course, for 70, 80 years. But previously, those were just built by government entities with very specific goals, or later on, then large communication satellites that did just kind of unidirectional communications down to the ground, just beaming a wide thing, and that worked. And given the electronics available at the time, that was pretty much all that could happen. But as you enter into the late 80s, I guess, and kind of early 90s, all of a sudden, electronics have been really miniaturized, become much more efficient, much more reliable, and digital optics started to kind of become a thing. And computers were getting faster, so you could do encryption, or you could do data compression, stuff like that. So all of a sudden, the market just kind of was starting to get tested by people like thinking that maybe you perhaps could launch a whole bunch of satellites, because previous to this, they're the size of school buses, and again, you need state level infrastructure to even support that, and much less even have a need for it. But along come companies like Iridium and I guess DirecTV and stuff like that, and they were able to kind of find the markets, sort of understood what it looked like, and were able to kind of deploy. But that really just waited out the clock a bit longer for electronics to get even better and better and better. And then all of a sudden you have universities where it's suddenly viable to launch somewhat inexpensively, because mass has decreased even more at this point, and things have just gotten more and more capable. You haven't lost any ground anywhere. And then you fast forward a little bit further, and all of a sudden we've entered in pretty much where we're at now, which is where all the pieces are there. They're all very mature. It's, can you handle the regulatory burden? Do you know your customer base well enough to secure the funding required? And these are no longer $20 billion programs. They're hundreds of millions. And you can launch a few, and then from that, test the waters and expand even further, and just kind of grow your constellation as you see fit. That doesn't necessarily mean the same thing to everyone. I mean, like if you're doing a comms network, say if you're like doing the space link sort of stuff, you're going to want continuous coverage pretty much right out of the gate. But if you're doing Earth observation, generating data and selling it to Google and that kind of stuff, you can kind of piecemeal increase your capabilities without really having a serious detriment. And And there's all sorts of markets that especially the Earth observation has opened up. Like you can, now that things have been up there long enough, you can start to look at how things are changing with time, be it landscape or the vegetation specifically. You can look at global warming, but you can use that as kind of a way to develop business strategies. And there's all sorts of stuff that the people with the mental acumen to do the business strategy stuff, they wouldn't want to ever build a spacecraft, much less conjure up a whole bunch of propulsion engineers to construct and develop and test a propulsion system. So that's where we're fitting in that regard.
So most of the satellites today are being launched for comms purposes. I know SpaceLink, I guess, is probably the most well-known, right?
Yeah, by and large, it seems to be the main target. Earth observation is up there, and then there's also some low bandwidth Internet of Things, very small, like Swarm Technologies has their little tiny bottle caps that they fly.
Yeah, I was reading something this morning that SpaceX has already launched, I think, of around 1,400 satellites for their SpaceLink initiative. And then I guess they have applications in there to launch tens of thousands of more satellites along with that. So just incredible to think of how many satellites are going to be up floating around out there. So,
and the low latency in low Earth orbit is very, very attractive, because if you don't have to deal with terrestrial-based fiber optics, and you can just take your infrastructure with you wherever you go, that is a tremendous, tremendous asset.
You've talked about the propulsion systems and things like that. So tell us a little bit about how that functions on the satellite itself and kind of what the purpose of function is for it on the satellite.
There's several different functions. Probably the most, I guess, in order of operations would be if you get dropped off, especially nowadays, you're going to go up probably in a rideshare rocket. So it's going to be you and all your buddies, CubeSats or 400 kilogram class satellites. And you're going to have to kind of crawl up to the orbit that you actually want to be at, where you're in the correct orbital altitude as per your FCC license and stuff like that, making sure that you're where you're supposed to be. So you're not just jetting around low Earth orbit causing problems. So you can use our propulsion technology to do that, to the orbit raising, if again, you're not launched in the exact orbit that you want to be. But the general purpose is actually station keeping. So basically keeping your satellite where it is supposed to be, assuming that you got there in the first place. And there's a lot of things that'll kind of work to degrade your orbit. I mean, you have these big solar panels, which are powering not only the propulsion system, but also the widgets that are making you the money. And while you're in space, the atmosphere is still there. So if you don't deal with it, your $100 million spacecraft turns into some girl's shooting star that hopefully she made a really cool wish that you got your spacecraft back. But in the more likely case, but also you have to deal with the moon and the planets. They kind of tug you around a little bit. What's really important is you just stay where you're supposed to be. That's important for the next thing is collision avoidance. Like if you start entering into an orbit or changing orbit rapidly, people won't really know where you are, so they won't necessarily know how to avoid you. They won't necessarily even be looking for you there. I mean, there's defense applications for that, obviously, but you don't want to be found. But generally speaking, it's kind of an agreement that just stay where you're supposed to be, please.
So what do they do when they launch a rocket, right? And they, I was, again, in that article I was reading, it was saying roughly about 60 minutes or 65 minutes after launch, they actually disperse these satellites into space. So do they release? And there's upwards of 100 satellites being released all at the same time. So do they release them and then these propulsion systems actually move them into their location and orbit?
I mean, it's difficult to say there's a one-size-fits-all approach, but to the first order, generally speaking, that's true. I mean, you'll get released off at different times. It's not like it doesn't just explode with a whole bunch of spacecraft coming off it. So it really depends. I mean, you're going to get a little bit of a propulsive kick being released. So if you're heading to a different orbit where the bus that brought you up is not necessarily going, then you could be reoriented and then get kicked off in that direction. But yeah, it's all carefully choreographed.
I found it interesting that it happened so quickly. You think about something going into space and you say, it must take hours, right? Or, a day to get there. But no, 60 minutes after launch, you're pretty much in orbit and you're able to disperse these satellites in space.
When you think of the time of it, yeah, especially you look at the amount of time that went into developing it and then bam, yeah, 15 minutes later, you just got kicked off and you're underway. It's pretty amazing.
The other thing that comes to mind is how do you test? I know that, for space applications, there's rigid qualification and certification tests that you have to go through. How do you perform that down here on Earth and qualify it for something that's going to be floating in space for a considerable amount of time?
As you might expect, it's pretty extensive test campaigns that need to happen. We build these large space simulation chambers. Gravity still works inside, so you can slip and fall in there. But the main goal of them is to simulate kind of the atmosphere of space. So we pull very high vacuum on that to remove any sort of influence that atmospheric pressure would have on these devices, because they don't work in atmosphere. Like, you cannot turn a Hall thruster on just holding it in your hand. So you need the high vacuum of space to prevent gas collisions and stuff like that. That's the only way you're going to be able to turn it on. So it's important that we on the ground test it to the best of our abilities. Unfortunately, we can't do it perfect. We're still stuck here on Earth, but we can get within like an order of magnitude of maybe of where we need to be. And keep in mind that we're already probably 10 orders of magnitude below atmospheric pressure at that point anyway. So we're kind of down in the noise. But one of the other key things is making sure that you survive launch, and that's actually quite challenging. Rocket launchers are very, very violent endeavors, especially if you're strapped to the top of it. They look neat, but they vibrate like an incredible force all throughout the launch, and the vibration testing that has to go into these is very, very rigorous. And then after that, there's pyrotechnics and stuff like that release different stages of the rocket. So imagine having something delicate that you care about, setting it on a big metal table, and then hitting it with the biggest hammer that you can find. Not the device, but the table. And that's kind of what a pyrotechnic shock looks like. And there can be multiple ones too. And on all different axes. So you really have to really test the mechanical stuff. Like the physics isn't the hard part. It's actually getting it to survive the launch and still work. I mean, you don't want to launch something that it left the pad as one piece and now it's just a series of bolts kind of just drifting in space. I'm sure it looked pretty, but not super effective at its intended mission.
I assume it must be difficult to do real tests too, right? I mean, they don't just allow you to put any satellite on a launch, right? So there has to be a specific mission associated to your device, right?
Yeah, correct. I mean, especially when you're ride sharing. Like, I don't want someone else's spacecraft. I don't want their propellant tank letting loose for no reason and taking ours out with it. But also, it's also being a responsible steward of space, ensuring that if things go really wrong, you can deorbit your satellite and it just won't sit up there as space junk. So it's been kind of an emerging international endeavor to figure out a way to, how do you enforce that worldwide?
Yeah, that was actually another interesting thing that they stated in the article, is just how many satellites are floating around up there that are non-operational, right? Thousands that are non-operational. I know that a few have made it back and had re-entry. Most of it burns up, but there are chances of pieces obviously making its way down. So I'm sure that's another issue.
And there could be some catastrophic solar event that could take out a whole bunch of them, and everyone will just be floating up there dead. Like, it's obviously a risky sort of environment, but you try your best.
So you talked a lot about your thrusters, and is there anything specific that makes them different and unique than what's already out there?
We've really sought to optimize it, so it's very efficient, very, very long lifetime, but that also is not necessarily a unique property of our thrusters. I think our main advantage is in how we, in addition to our kind of testing plans and just kind of the general robustness of the stuff that we do, but it's our ability to manufacture the same thing more than once. So again, previously, these thrusters were manufactured maybe 2 or 3 a year by huge companies, and they would charge millions and millions of dollars for just the thruster alone. Because when you're out selling more than a couple of them, you still need essentially the same number of people. The cost is going to just skyrocket. But for us, since we're kind of making it up in volume, we brought on contract manufacturers, and they're people who love following procedures. Bless their hearts. I mean, they're the kind of the exact opposite of kind of the engineers who helped create it, because the last thing we want is someone doing a little bit of just-in-time engineering on a flight unit. It's like, nope. We let these people who follow procedures precisely, and we get the same thing every time, which reduce the subsequent testing costs, because if we can guarantee and certify that this is precisely the same as the other one, the testing requirements start to kind of drop when you get to a serial number above, say, 10. Like, the first 10 worked flawlessly and exactly as predicted. So you can start to throttle back some of what might seem as a little bit risk averse, but that really depends too on who the customer is.
You touched on something there that I find interesting, especially as a startup company, as being really challenging. And, in this field, it's got to be even that much more challenging in terms of getting yourself established and taken seriously by the industry, right? To the point where people are going to be, like you said, there's other companies that produce thrusters. How do you get through that? How do you get taken seriously by the other large players that are in this area, in this space, no pun intended, in this area? And actually, then you mentioned production as well. So if you can touch a little bit on how do you get a production facility that is going to be serious enough that they're going to produce a product that you can actually deploy.
Yeah, so our approach on that was to build the whole thing for manufacturability from the outset, to make it, I wouldn't say necessarily simple, but make it so it can be assembled in a way that it's not impossible. It doesn't require an understanding of all the physics that's going on. So long as you follow the instructions, you'll be just fine. And by going through that whole process, what that did is made us attractive to those customers that actually are more risk averse. So the bigger spacecraft, like the ones that, the $1 billion class ones. By essentially meeting all those needs, by default, then we've met the needs of smaller, more risk ones with a higher risk appetite. So it just kind of killed two birds with one stone, and one of them, it had to be done anyway. So we just did it from the outset. How we're taken seriously, again, just we deliver a mountain of paperwork, give tours of lab facilities, and just kind of point to the veracity of the entire design process. Like no stone was left unturned. Like there's no secrets. And if you think we have one, please let us know what it is so we can mitigate any concerns, because we want this to work just as much as everyone else does. So, I mean, our success is predicated on theirs. So.
Yeah, I think it would be interesting for people listening to this, especially if they have startups of their own. And how do you kind of break through and break into the industry and again be taken seriously? I think your CEO actually had some experience from his prior employer, right, in kind of this general area, right, which probably helped as well.
Yeah, I mean, Mike worked at Google as a VP on Project Loon and ran that for quite a while. So. Yeah, getting people to take the technology serious, and primarily the telco operators and stuff. Like, really, you're going to fly these balloons, and you can steer these balloons at high altitude. So they went through the same sort of thing. Like, you have to prove it out. Unfortunately, there's no real shortcuts you can take in aerospace because those never end well. So it really is just. I make this joke, like the only way to get to space is on a mountain of paperwork.
I can only imagine all the governmental regulations and big corporate stuff and certification and everything else that goes with it, right?
Yeah, there's a tremendous amount on the line, and mistakes, could, again, dead satellite on orbit could persist for a very long time. So you don't want to be that guy.
Yeah, absolutely, I can get that. So, what do you see as the goals for Apollo moving forward, looking into the future? I mean, obviously, become successful. We all want that for Apollo. So,
yeah, sure. Looking forward. I mean, we have customers signed, so we're starting to deliver flight hardware now. If all that goes well, which there's no reason to think it won't. We'll continue to push our main product, which is the ACE thruster. We're currently not all set up to be a one size fits all. Like, we have a lower limit on the size of spacecraft that we can propel around because it would be too powerful, and then also an upper limit because it wouldn't be powerful enough. So we can expand in both directions. It's just more of a question of which way are the customers going to want to go. And now that we've established ourselves as a company that can deliver, we'll have no problem picking a direction, or both directions for that matter.
And you have a launch coming up, right? Is this your first launch?
Yeah, this will be Apollo's first launch. I mean, others on the team have many spacecraft in orbit, but as a team, this will be our very first. So, funny story, like actually right after we finished recording this podcast, I'm going to go load propellant into the spacecraft.
Oh, wow.
Yeah, so then it gets shipped off for integration, and then should launch coming up here in a few weeks. That's
phenomenal. Congratulations on that.
I mean, it's exciting, but it's at the same time, it's like, I can't wait till that thing's in space so I don't have to look at it again.
So, in a good way, right?
Yeah. I mean, the first one's always the most difficult, and we learned just a tremendous amount of procedures and this kind of stuff, how you do it, how you interact with, the different customers who sometimes they themselves are going through it for the first time as well. So it's been great. I mean, the space community is pretty fantastic. So.
Yeah, I get that. It seems that way. And again, talking, assuming that we have an audience here that are people that are startups or looking at developing a company or starting a company, what challenges do you see looking forward from not only from just a technology perspective, but a business perspective? And what advice might you share with those folks out there?
The business challenge is really understanding your customer, like understand their pain points. A perfect example of this is we wanted to make a thruster where, like, here's the power level, this is the performance, and we have like one SKU for this. This is what we got. And then we were hoping that our customers would use that then as an anchor. Like, okay, great, we have propulsion solved. And then you can start to wrap the rest of the spacecraft around the propulsion system. Because there's so many different variables, like how much power you need, all this kind of stuff, that when it's so unconstrained, it becomes overwhelming, difficult, and that's how cost overruns happen and stuff like that. So we were trying to just give like, look, this is our offering, the way it works, and maybe it won't be good for you, but this is what we got. So if you can design around it, perfect. And that strategy has worked by and large, I think. Reducing the strain on the customers, because they're going to have someone who's going to be like, okay, what are we going to do for propulsion? And they're going to go off and try to find, the best thing out there. And we're just trying to help them our way, of course. But, if we're not the right fit, let them know right away, because we don't want to sell things people don't need. From a technical standpoint, everyone who knows me will laugh, but I mean, documentation is very important. You'll remember it for a while, but not as long as you think you'll need, or not long enough. But I mean, building a good team and good communication, good management, having fun at it really goes a long way to address any kind of challenges. Because then you're not dealing with it as an individual. It actually feels like a team, and you're kind of all in it together.
So I'd be remiss if I didn't ask you before we leave. So what drew you to Siemens and the products that you're using from us?
In the earlier days, right after we pivoted to thrusters, I was giving a former mentor of mine a tour of the lab, showing him the thrusters and all this kind of stuff. And he was like, wow, don't you guys just keep looking around here trying to find that framed picture of Edison based on how you guys are kind of going about this? And I'm like, haha, that was funny. And to some degree true. I mean, at that point, we were working kind of on the physics side of things, which didn't have much to do with getting it to survive launch and all this kind of stuff. Like the practical stuff we hadn't really arrived at yet. It was more like, getting kind of correct dimensions of the physics payload. But he was right, though. I mean, like, we weren't really using that many engineering tools aside from CAD, rudimentary, analysis when it came to thermal, and also to like vibrations and later on for shock, just to kind of see if we're heading, in the correct direction before we really drilled down into it. And those tools eventually weren't quite up to the robustness that we required. So that's how we kind of landed at using Siemens and the NX platform for our stuff. I mean, it took a substantial effort to go through and actually build all the models correctly. And we were able then to turn around and use those models to improve our design, because there were some deficiencies that we hadn't really thought about, or some things that interacted that you simply just haven't considered. When you have a whole bunch of parts, you really can't understand how part A is going to impact part Z in a way that, I mean, if you can wrap your head around that, that'd be amazing. But that sort of stuff is actually getting the right tools for the job. But so far as the Siemens startup program goes, that was actually truly enabling, because without that, I don't know what we would have done, because that was going to be well outside of our grasp, because we don't have institutional cash laying around. So it wouldn't have gotten done, or it would have gotten done back to the Edisonian way, where like we would have to vibe it and see what broke, and then try to figure out why it broke. And that in itself is also expensive, but more importantly, time consuming, because you can sit there at a vibe table forever and never really get a solution, when you can sit at a computer for maybe a few weeks and truly understand the problem, mitigate it, build it, and then you'd be actually ahead of where you would be if you spent a whole year at the vibe table.
That's awesome. I appreciate it. And it's been great working with Apollo and working with you in many ways, and getting to know you has been fantastic.
I've really enjoyed this.
Any parting words for our budding entrepreneurs out there?
Yeah, don't give up. I mean, there's nothing wrong with failing, trying again. Like it's all okay. If you give it your best shot, there's absolutely nothing wrong with not succeeding.
Apollo serves as an inspiration to many. I mean, this is no small challenge to take on, and it's a tough industry to crack into. So the fact that you're having success is fantastic, and congratulations on that. I mean that. As
much as I complain about aerospace, I mean, it has been a lot of fun. I mean, it's an intimidating field for sure. You have to be prepared for that. And people ask tough questions. You really can't just let anything glide by. So, but just be prepared. And if you don't know, just say it. Like that's the thing.
Thanks, Dean. I appreciate it. We'll wrap this up now, and we sincerely appreciate your time and the relationship that we have with Apollo. It's been great, and I appreciate you taking the time to do this today. I know that you're really busy and you're under really, really tight schedules and deadlines. So I just can't tell you how much we appreciate it. So
yeah, and thanks, Paul, for like reaching out and kind of getting our message out there. Because again, Siemens has been fantastic. Our local vendors, ATA, and all them have been just spot on the entire time. So.
Yeah, that's great. Let's do a shout out to ATA. Those guys are fantastic. So I want to thank everybody for listening to today's podcast. At Siemens, we understand that getting a startup off the ground is not an easy endeavor, and understand the challenges that early startups face. So we are really, truly striving to help entrepreneurs turn their ideas into reality and meet their full potential. We have many startup customers that are making a difference, and we are proud of all of them. It is our pleasure to tell the stories and inspire other startups. And if you have an idea for your own business and looking for a partner, please visit us at siemens.com/software for startups to know how we can help. So this is Paul Musto. Thank you for listening to our startup podcast. Again, please let me know what you think of this episode by leaving a review on Spotify or Apple Podcasts. Again, or you can email me directly at paul.musto@siemens.com. And we hope to have you in our next episode. And remember, innovation has no boundaries. Thanks, everybody, and goodbye.